The following program is brought to you by Caltech.
Thank you so much, Michelle, and we just want to give everyone here a very warm welcome to the public lecture here this evening as the public outreach section of our new workshop, new study on airships, a new horizon for science. So in the last decade, there's been a really interesting, exciting resurgence, renaissance really, in airship, high-tech airship design and development, and it's such a tantalizing opportunity for scientists. Naturally, we think of these things as potentially excellent platforms for very unique science that we could not do otherwise. And so tonight we have Professor Robert Fesen here, a professor of physics and astronomy at Dartmouth, who's also been associated with University of Colorado Boulder, NASA Goddard Space Flight Center. He's been the acting director of MDM observatories at Kitt Peak, and he's also been on the board of directors of the 10-meter SALT telescope in South Africa. And really, he stands out as one of the scientists who's been thinking about how to use these new high-tech airship platforms for science longer than almost anyone. And we're very excited to see, we're very excited to welcome here tonight to really give you an outline of the very exciting possibilities and future of airships for science. So please help me give him a warm welcome. Thanks.
Thank you, Sarah. I'm Rob Fesen. I'm from Dartmouth. I'm going to just run through a review of where we are in airships and why we would want to have an airship, what sort of science we can do. You probably know that we can do science from high-altitude balloons, and we've been doing it for a long, long time, over 70 years. We use a huge, massive, multi-million cubic foot balloons, launched typically from Antarctica, sometimes from the Arctic. Sometimes even over more remote regions of the Earth where people live, like Australia. They fly in altitudes of excess of 100,000 feet, and there's a reason for that. I'll go over that in a second. But scientists have been using high-altitude balloons for a long, long time. We are still using it. NASA has a big balloon program to do that. This is just a quick table. I don't expect you to read everything here, but here is altitude in kilometers. This is altitude in feet. Pressure millibars. At atmosphere of 1 atmosphere, it's just over 1,000 millibars. Density, temperature, you don't have to worry about those. But the point is, we try, in an airship design, try to fly something up very high above the weather. Above 60,000 feet, there's basically no real weather. So if you're at 65,000 feet, you're above, well, that's 55 out of 1,000. You're above all but essentially 95% of the atmosphere. Only 5% of the atmosphere is overhead. So, and that is 19.8 kilometers. That's 12 and a half miles. So where we try to fly these things, or like to try to fly airships, is at a modest height in the atmosphere of the Earth. And we sometimes call that near space. Near space, you can define it different ways, but when you get above the air, where most pilots fly, even high-altitude reconnaissance aircraft, they don't get much above 65,000 feet. So this big region here, 65,325, is sometimes referred to as near space. It's not space. Air density is extremely low. It's hard to fly high-altitude planes. And above that, you're really in the space. If you want to become an astronaut, you need to get above 325,000 feet. Some X-15 pilots were actually the first astronauts because they flew the X-15 above 300,000 feet. And it's a great spot because look at it. At 65,000 feet, 20 kilometers, 12 miles, you're 25 times closer to the Earth than a low orbiting Earth observatory like the Hubble Space Telescope or satellites that normally go around the world in about 90 minutes. that are up around 300 miles, the International Space Station around 300 miles, and you're 2,000 times closer than geosynchronous satellites, the weather satellites, the satellites that take the photographs every day to see what the weather patterns are. So you can get 2,000 times higher resolution of features on the ground from a geosynchronous satellite, or 25 times better than the International Space Station, for example. That's impressive. What you can't do is some sort of science that involves X-rays or UV, ultraviolet light, because we have this ozone layer. And this is in altitude in kilometers. Again, it's a low-resolution picture, unfortunately. But you can see we have pollution of ozone down low, industries, people. Then you go up to 15 kilometers up. And then the ozone layer really comes in at the lower part of the stratosphere. Stratosphere is ozone. It's wonderful for us. It keeps us from needing sunscreen 5,000 if we didn't have the ozone layer. But to get above the ozone layer, which absorbs ultraviolet light, you need to be up at around 30 to 35 kilometers. That's 120,000 feet up. And that's why the NASA balloons go up to that altitude to get above that. So you can do X-ray, you can do UV, you can do a whole bunch of other stuff. And there, you're above 99.9% of the Earth's atmosphere. We've been doing these big balloons for a long, long time. They're so heavy payloads that, in fact, you need a crane to lift them up. There's long trains of uninflated balloon here that will eventually inflate at very high altitudes, the float altitude, 120,000 feet. The balloon fabric is extremely light and tenuous. The weights are 1 to 2 tons. Typically, balloons can go up to 130,000 feet. There's been a Japanese study trying to get it up to 160,000 feet just as a PR shot. That's really high. It's still not space, technically, but it's very high. The problem is, if you do these sort of things, you have a really heavy payload, which gives you a lot of latitude in science. But the platform is bobbing and weaving and twisting as it's on this long, long tether. And they also drift with the wind. And so what we can't propel these, we can't maneuver these things. And so what we do is we let them drift. And we let them drift around the poles, typically Antarctica. And this is a big balloon payload. You can see the scale of the people there. It's being held by a truck. And off to the side in the background, there's a big, huge balloon about to be inflated. So they're massive. We still do these. This is just a slide I took from some NASA administrator talking about how wonderful a balloon program is, and it is a really great balloon program. They lift big payloads. These are, I won't go through the names, but you can see the payload would be down here. This is BLAST. I'll mention that in just a few moments. But this long, uninflated balloon here, there's a parachute here, and what they do is they want the payload to come down. They'll cut the parachute off from the balloon, and then it parachutes down, and they can get it. They can fly since around December of last year. They flew a total of 96 days. This thing called Super Tiger. The principal investigator was the person at Washington University. BLAST is another project. Mark Devlin at the University of Penn, he's the principal investigator. They do these various scientific programs, this mapping of the polarized dust emission along the Milky Way plane. Great science, astrophysics science typically, and a variety. And what they do, they can't push this balloon around. They have to let it just float and go where the wind takes it. And the polar winds are around the pole. They go around the pole. So for like the Super Tiger project, it went around several times, 55 days, 1 hour and 34 minutes. Well, here's BLAST, 16 days. These are long projects, weeks. That's what you want. You want to collect a lot of data. Great. We'll just examine one of these balloon projects, BLAST. BLAST stands for Balloon-Borne Large Aperture Sub-Millimeter Telescope. And here's Mark Devlin, University of Pennsylvania. He was the principal investigator on this. This is the payload in the back. You can see it's a large structure. Here's the balloon as it's being inflated. And he took this picture. You can see the Antarctic mountains in the background. Difficult place to work, but you get long flights and you don't have to maneuver the balloon at all. And NASA provides you with big envelopes that go up very high. This is the telescope, and the light would come down, bounce off the mirror, go up to a secondary mirror, and go back into this instrument pod back here. And that's what they were doing. That's a standard astronomical infrared telescope assembly. Very heavy, several tons. You can compare it with the ladders. This is a big thing, and we have to lift it on a balloon lighter than air. We have to get it by buoyancy. So we have to displace the same weight as the payload. We have to displace that amount of air. That not only just the payload, but the balloon itself. So we make gossamer thin balloons. BLAST telescope weighs as much as a Hummer. And as Mark Devlin said, both are available in red. Not quite, but it's a big SUV you're launching up. And then you have to maneuver it in the sense of focusing on the targets you want to do, get the science for. This is it. This was one of their, they had a flight in Sweden in 2005. This gives you the scale of these things when they're inflated. They're gargantuan. This is the Washington Monument. This is as it goes up at launch. You saw the long uninflated area of the balloon, the parachute, the payload on the bottom. You know, this is 620 feet from here to here, another 310. These are colossal structures. And you have to be very careful with that balloon fabric, of course, it's so thin. When it gets inflated, it looks something like that. It's a football stadium-sized balloon. And, you know, again, it's very big. This is what they flew. There it goes from Sweden over to Canada, and it landed, and they recovered it. And they had to cut it down because it was going to go eventually over water and then maybe over Russia, and there was no fly zones over Russia. It face-planted itself. It damaged the mirror. They broke $1 million mirror. Bummer. Well, that's the cost of trying to do science of a high-altitude balloon. But you get the science, but it's tough. So they moved to Antarctica. And this was, they've done a flight recently, and I think that was the fourth or maybe the fifth flight just this past few months ago. The first one worked very well. It landed just perfectly upright. It was perfect. Second one, they lost the mirror. The third one, here we go. Here's the movie of it being released from the balloon and the parachute coming out. Here's the parachute. Now, when the parachute lands, it doesn't deflate necessarily. Antarctic winds can be pretty high, and it started to blow the payload all across Antarctica. How far? Very far. What happened? It tore it apart. The payload, it tore it apart. And they kept flying farther and farther out every day to see where the payload was, and they had stored the data. You couldn't communicate to it, so they had to get the data, what they were collecting, and put it on hard disk, and they put it in hard, big metal cylinders. And this is part of the balloon gondola system, and they found that part, but that did not contain the data. No data. So they flew a little bit farther. They found the parachute. Well, somewhere along the line must be the data. So the science payload was dragged for dozens of miles across the Antarctic terrain with the data disk 75 miles. Really? Seriously? There it is. There's the data. And this is the metal cylinder that contained the data. There's got to be a more elegant way to do science. Dragging your science instrument across the Antarctic plain. You have no control over the vehicle. Come on. All right. How about an airship? An airship is a balloon that has propellers on it. You can push. And this is a balloon, an airship that was built by Lockheed Martin for the military. And really what an airship it is, it doesn't show here the propellers, but this was just inflating it in a hangar. An airship science might carry less massive payload because obviously we're not going to have millions of cubic feet and try to push that huge balloon through the air. So it's going to be smaller, hence carry less. You're not going to probably get up to 100,000 feet. You may not need to get up to 100,000 feet. But because it's maneuverable, it doesn't have to be around Antarctica or the Arctic or Sweden or northern Canada. So what are the advantages of an airship? Airships are maneuverable, so you can do maybe station keeping. The military paid a lot of money to Lockheed Martin and other companies to build an airship that could stay in one place roughly over a course of many months, maybe even a year, over continuous nighttime day operations. When you fly into Antarctica, you fly during the daytime, the Arctic summer, and that means you can't do nighttime observations. You can't observe stars. You can observe the sun, you can do X-ray observations, cosmic ray observations, microwave, background radiations, things that the sun doesn't interfere with, but you can't do it in the polar regions for UV work or optical work. You can't make nice, pretty pictures of the sky in the optical. Wide latitude ranges, so you can maneuver, you don't have to be the polar, and simple line of sight communications. You don't have to store the data on hard disks. You can get simple line of sight communication. Disadvantages, atmospheric density limits. You can't push a balloon if the density is not enough to push on. So you're limited to about 90,000 feet, and you hence are below the ozone layer, so you can't do UV and you can't do X-ray. And practical payloads, as I mentioned, can be much less than that of the NASA big, huge balloons. And you may not be able to station keep all year round. Winds at stratospheric temperatures, stratospheric altitudes rather, are fast. Some areas at 60, 65,000 feet, they are slower than low altitudes or even much higher altitudes, but they can be ferocious at some times of the year. When we think about airships, you might remember about this. That's not a good advertisement for doing science on an airship, but that was a hell of a vehicle, amazingly designed. We had fleets of airships, what we normally refer to as blimps. The Navy had lots of them. This is the fleet of them. And airships were used after the Hindenburg disaster in 1937, but for the most part, it was the United States because we had the helium supply. Other countries didn't have the helium supply. And by the time World War II began, the United States had a blimp division. It was the only country in the world that had a blimp division. We don't have blimp divisions anymore. There are two regions in the atmosphere you can have a movable, lighter-than-air vehicle. Airships can operate below 20,000 feet and above 60,000 feet. Why nowhere else? Well, this is the wind speed in knots, a little faster than miles per hour. And this is the altitude in feet above the ground level. So here's the wind. This region here in the blue indicates the average speed, but then the variations is the blue area. So at 30 or 40,000 feet, the winds can be 80 knots. That's almost 100 miles an hour. You can't push a big balloon and stay over a station-keeping sort of balloon and stay over one spot when you're pushing on a big balloon and the wind's blowing at 100 miles an hour. That's not going to happen. So this area is really hard on an airship, not possible. And you can do it low down, and blimps have typically operated below 5,000 feet. A few thousand feet. Goodyear blimp, 1,000, 2,000 feet. And then this is the area that we actually might be able to do an airship of, if we can build it big enough that we can displace enough air and lift something meaningful. There's also turbulence. This is the curves of probability of turbulence, atmospheric turbulence. Again, amplitude effects in feet per second, how much you get jostled around, and this is altitude in thousands of feet. And you can see up at above 60,000 feet, things calm down a little bit. Whereas you're 20, 30,000 feet, things get very bad. If you've ever taken a flight across the United States, you know, sometimes you hit the jet stream and things get and you try to type on a computer on the little seat back, and you just can't do it. And then down here, airships can fly very nicely. It's not too turbulent along the ground. Have we ever built one of these? Yeah, we built a bunch of them. The holy grail of the lighter-than-air community, LTA, lighter-than-air community, is essentially an airship that can propel itself. And this is a couple people standing here. This was built by a company that builds balloon fabrics. It was Raven Industries. It was in the late 60s, I think 1967. It was built to fly at about 20 knots. It was supposed to last for 6 months at 70,000 feet. It lasted, I think, 7 hours. I had two flights, one 2 hours and one 7 hours. That's not a big success. And the vehicle, I don't think you can see it here, but it had solar panels down here, and the payload was hung down below. It looks like a torpedo. It looks like an airship, but very thin membrane and to go up. In the last 10 years, there have been a lot of excitement, mostly on telecommunication people side and military side, to develop big airships to sit and loiter over an area. The military is big on persistent surveillance to see what's going on. Flying planes in and out is very costly, very time-consuming, and airplanes are expensive to fly. If you had a balloon just sitting there, that would make a lot of sense. We've got a whole bunch in the last decade of different designs of airships. Some round, some dual hull, a V-shaped thing, a big torpedo shape, mostly torpedo shape to limit the drag on the vehicle. The commercial people got very interested in this around the late 1990s and early 2000 area. Korea was involved. They wanted to do it. Japan was involved. These are just telecommunications. Why? Because you can do internet at 65,000 feet. And for third world countries or remote areas, you can have this thing sitting overhead and have communications to it. That would be great. Can you do it? Well, a lot of those programs were started, designs were made, and they pulled back a lot because, well, the Department of Defense of the United States were throwing lots of money. So they sat back and watched, see what happened. And some of them really didn't, they closed down. Japan had a whole series of working its way up. Nothing came out of it. There's this one company called Sandswire that was based out of Washington, D.C., getting a lot of money from backers. It built this big vehicle. As far as I know, it never flew. They went bankrupt. Then they moved to Germany, and they built tiny little airships that fly over about a few hundred feet. So they went from this to being toy balloons, basically. At 65,000 feet, you have really persistent surveillance over a large area. Radius of 300 miles. And the DoD wants this thing called Intelligence, Surveillance, and Reconnaissance, ISR. If you've ever read any military Aviation Week and Space Technology, they talk, there's all these advertisements of these companies talking about what they can do for the military for ISR. And this is how Lockheed Martin responded. They were going to build this high-altitude airship, the HAA, and you could do communications, you could watch missiles going off, you could confer with the ground troops, see over the horizon, you can tell the ground troop that what's going on, you can communicate back to the base. Perfect. Station keeping, high altitude balloon, better than an airship, than an aircraft. And it just so happens that at 65,000 feet, you could cover almost all of Afghanistan. So there were a lot of push. There was a big push by the military to do exactly that, to put an airship hanging over Afghanistan and work a large area for reconnaissance, intelligence, communications, and reconnaissance. There's been also a big push. You might have heard stories or watched TV. They've had stories about big airships, not to do this ISR at 65,000 feet, but to do low cargo or troop movements. Because if you displace air at ground level, you can get a lot of weight lift on these things. And so Lockheed Martin made this thing called the P791. It was going to get up to 20,000 feet, carry up to, at low altitudes, 20 tons. Northrop Grumman built this thing called a Long Endurance Multi-Mission Vehicle. It was going to go 21 days, up to 22,000 feet. And then there's this company just south of LA building this huge vehicle. This is only the small demo version. And they hope to lift something like 60-ton payload. And eventually up to even 500-ton payload. All right, well, that's a different sort of airship that we were talking about for science. But if you look at Aviation Week and Space Technology, this was in the papers, in the trade magazines, persistent surveillance. What's next in line for long endurance UAVs? Both from the side of high altitude aircraft, but also from airships. Rise of the airship, that was one of the cover stories, and big balloons. If you go down, how much money have we spent on this? How much the US alone has spent? We had that, we have this thing called the Blue Devil. Actually, it's not this company, it's Northrop Grumman. They bought that. They built one of them. Its operational altitude was 20,000 feet at $243 million. That's not quite true. They didn't spend all the money. They didn't get all the money. The military, after a while, cancels the program for a bunch of reasons. So they never complete the task. Lockheed Martin built the HAL-D, and I'll show you a movie of that in a second. It was supposed to go up to 60,000 feet. Just to build the device, the airship, was $36 million. It's expensive. It turns out to be really hard to do this. Lockheed Martin also got DARPA, which is the Defense Agency for Research, money, and that was up to $500 million. That was about the same altitude range. Northrop Grumman built the LEMV, 20,350. Whoa, all these things. These are small potatoes down here. And then these are aerostats. Aerostats work. Aerostats are just balloons on a tether that you can lift up to a few thousand feet and survey one area and just fight the wind. And if the wind gets too bad, you pull it down and then you put it back up around. They've had dozens and dozens of those in Afghanistan and around the US border. And they work extremely well. They are still very costly. Each one is like $10 to $20 million. And we've spent billions on that. But these are low altitudes. These are the high altitudes. And the high altitudes for science, in some regimes of science, is very important. So this is the Lockheed Martin high altitude HAL-D demonstrator. So it's high, H, A, altitude, long, L, endurance, E, demonstrator. So here's the movie. I hope it shows. Come on. So this is the vehicle that Lockheed put out. Look, it's a gorgeous airship. Let me move the cursor out of the way. And it goes up. They release it. There's little propellers. It was supposed to go up to, there's the propeller running. They have lights on it. This was the morning, and off in Akron, Ohio. Big airship. This was only a small demo, though. This is a demonstration. The payload was something like 80 pounds. That's all. Well, of course, the lift is the balloon itself and all the auxiliary control systems and communications, but that vehicle almost made it. It had a technical problem. It had to be pulled down, cut down, essentially, after it only reached 30,000 feet. It was a glitch, a small glitch. If it didn't have the glitch, we all think that it would have gone up to 60,000 feet and probably been up there for weeks and maybe even a month or two. Near space starts only 12 miles away. I can walk 12 miles. I can take my Honda Civic and drive 12 miles in 20 minutes. Why is it so hard? It's 12 miles away. Well, what's been the problem? Well, station keeping, you need a lot of energy. You have to have either battery power or some solar cells going on, or power cells that you keep to run day and night. High altitude winds can be very strong, so you have to have a lot of propulsion. And the winds, to just show you what the winds are, these are plots with the function of years, 1987 to 1990. And the plots, this is like the 50 percentile is down here. Half the time it's this speed, and 99% of the time it's going. And this is the wind speed in meters per second. What's meters per second? Multiply it by 2 and you get miles per hour, roughly. So sometimes at polar regions, between 66 degrees and 90 degrees latitude, it's over 120 miles an hour. You can't fight that. That's insane. Now, it's only happening a few times a year, but the rest of the year, it's over 20 meters per second, 40 miles an hour, 50 miles an hour. That's tough. You can't do it. But it's perfect for big balloons to go around the poles. In equatorial regions, it's a lot less. The scale is now shrunk. You can go up to 50. It was 50 over here. Here, you actually have winds that are only 10 meters per second. Equatorial regions are much, much better. But the problem is, it's not just the wind. The higher up you go, the bigger the vehicle you need. And the bigger the payload mass, the larger the balloon is. And the bigger the airship is, the harder it will be pushed against the stratospheric winds. So everything that makes more weight, like the balloon to go up high, is more weight. So now you need more propulsion to push that big balloon, and that's more weight. And it just feeds on itself. And if you do a plot, if you're talking about thousands of feet, altitude, so altitude now is on the x-axis, and here volume of how big the balloon is in millions of cubic feet. The balloons, as it says, for altitudes above 70,000 feet, so the balloon gets bigger and bigger and bigger. If you have just a 20,000-pound payload, 60,000 pound, whatever, these things become spectacularly big. You can't do this. So you must keep the weight down for this to even come close to working. Well, and we haven't been successful so much with the Department of Defense rather, because development costs have been a problem. The customer, it turns out the Department of Defense is a very fickle customer, and they keep changing their specs. They had originally for the HALE-D and high-altitude airship amazing specs, ridiculous specs. You would hear about them and you go, this is just silly. No one can do this. And they kept changing, and then they would get the airship manufacturer would get very close, and then they said they would change people who were in charge of the program, and one person liked it and one person didn't, and they would cancel the program, and then it just fails. Why not use all that money, though, the designs, the experience, the lessons learned from like the HALE-D, and use and to produce a scientific, not a military derived airship. And we can have not big, heavy payloads. Keck Institute for Space Studies has had sessions, workshops on small satellites. We can do great science with payloads that don't weigh as much as that BLAST payload that weighed several tons. That was as big as the SUV. So it turns out there is a suite of science you can do, even with blimps. Blimps, we know how to build. We fly them, Goodyear blimps. And there are a few blimps that are available for purchase or rent. You can fly them. Well, what can you do? Now, I'm already talking, as I said, there's two avenues to do airships. You can do low altitude, below, say, 10,000 feet, maybe 20,000 feet, maybe even 25,000 feet, but with smaller payloads. And then 60,000 feet and above. So what can you do at low altitudes? Not so much astronomy, but a lot of atmospheric work. So airships, what you might call blimps, are currently flying that can obtain a lot of very, very valuable data for atmospheric and earth science studies. One is understanding the pollution associated with large urban areas. These circles and dots are indicating areas of large areas of concentrations of people, and the idea is the urban dome carbon monitoring. You can do that with an airship. You can't do that so easily with an aircraft because it flies in and out. Have a station-keeping blimp. We know how to do that. You know, the Goodyear blimp flies over stadiums, and that's station-keeping, and you can monitor the air over a large city for days, maybe. You could bring it up and down and refuel it or whatever, and you can do it for a long period of time. And we have airships. Some of the airships that were developed for the military can fly for days and fly up to 20, 30,000 feet, maybe up to 22,000 feet. So that's one very practical, very down-to-earth use of an airship. Another thing is, a part of that is you can study gas concentration, study pollution. You can merge what you get from airships with other sensors, space sensors, aircraft sensors, and you can do air quality predictions. That's really what you need. You need a spectrum of data to put this all together. Airships give you some information, maybe not all of it on a larger scale, but they give you the smaller region over a city. And you can fly airships over cities for long periods of time. We've talked about that in the current workshop. And then you can do maybe studies of ice changes, dynamical climate changes in the Arctic Sea. You can fly these things over. It's hard to do that with aircraft. They're in and out. They have a few hours altitude, duration flight time. There are a couple aircraft that can fly 20 and 30 hours without nonstop, but they are UAVs. This could be manned. You could operate it. You could figure out that a particular area that you're interested in flying it not for just 20 or 30 hours. You could fly for days. That's a big sea change in what you can possibly do. And you can't do this with low Earth orbiting satellites. You have a 20 times better resolution than flying it with an orbiting. You could sit over the area of interest. Other things you can do that you can't do very well from space or aircraft. High altitude airship science. We like to know how things transport between the troposphere, where we live, and the stratosphere. There's the tropopause around 40,000 feet at mid-latitudes, and there is a transfer of things. Like in a thunderstorm, there's convective flows, and you can get, including things like water up, and we'd like to know how things go up as well as things come down. If you have an airship, either flying at 10 or 20,000 feet, but maybe also at 60,000 feet, you can study that in detail. You can sit there and watch it happen. You can't do that with an airplane. That's really impressive. There's also lightning. You might have heard about 15, 20 years ago, we found that the lightning is not only directed down to the Earth or cloud to cloud. There's big, and I mean big, lightning bolts that go up to the ionosphere, And we only discovered that there were airline pilots that would report. They would see lightning flashes out of their cabins at night when they were flying over the oceans, and they would see flashes, really fast flashes. You know, they would ask, did you see that? They're real. We photographed those, and they're amazing. And they're called blue elves or red sprites. And look at the altitude, 50, 100 kilometers up. Whoa, way up. And to photograph and study these things, they're very, very fast. And there's discharges from thunderstorms. And we've seen this from space now. We can see sprites from space. But it'd be really nice to have an airship at, say, 60,000 feet and watch this. So this is moving into the higher altitude range. And watch the thunderstorm perform for us. And I'll just show a picture of red sprites. These were taken from the ground. It's amazing stuff. Lightning bolts, and they are not single bolts. They cover many square miles going up. That we didn't know 20 years ago, and we'd like to know a lot more about sprites. And it's actually a worry for high-altitude airships because they're going to be in this lightning show. The military worried about that. It shouldn't be too much of a problem you can protect about it. But this scale here is in kilometers up. These are big lightning bolts. That's stunning. So that's the thing you can do. And lastly, for atmospheric science, you know, if a volcano blows up and has this plume of material, you could use airships to study that. Really. Yeah, you could fly in the plume that you cannot do with a turbofan engine because it will destroy the engine, all the dust. You could fly through that thing or stand back and watch it all happen. And as it went up, the plume went up, you could follow it up as far as high as you could go with the airship. So there's some really great atmospheric studies you can do with airships at very low levels around cities and in very high altitudes. And the NASA scientists, the atmospheric scientists, have realized this for years. They've been flying high-altitude planes. This is a high-altitude plane about 60,000 feet. This is the NASA version of the U-2 aircraft that flies about 70 or 75,000 feet. And I don't expect you to read this, but there's lots and lots and lots of science projects on high atmosphere projects using very high altitude aircraft. So if you had a high altitude airship, there's lots of science you can do. What about astronomy? We're in a building that's dedicated to astronomy. What can you do with astronomy? Planets and stuff. Well, if you're up at 65,000 feet, as I said, you're above all but 5% of the atmosphere of the Earth. That should produce very good quality imaging. Is it high enough? You want to be like in space. Doesn't that picture look like you're in space? No, it's the picture taken from the window of a U-2. You're up pretty damn high. You don't have to get up to 120,000 feet. 99.9%, 95, 96% will do me just fine. I don't need to get up that high. This is the wing of the U-2. That's interesting. And there's the little picture of the U-2. You can see the tank. I haven't found out whether it's a tank of fuel or more instrumentation. I believe it's a instrumentation pod. Huh? I believe it is instrument pod. Although they have, on business jets, sometimes they have pods that look like that, and that's just gas tanks. Okay. Well, a telescope mounted on a high-altitude airship, that would be a game changer. Because with the right instrumentation, you would have a very powerful observatory. The Hubble Space Telescope is not a very big telescope. It's only 2.5 meters across, That seems large by amateur standards, but for large ground-based telescopes, that's actually sort of puny, moderate size, small. What makes the Hubble Space Telescope powerful, so powerful? It is in space. The image quality is exquisite. It's a perfect mirror, as good as mankind can make a mirror, and we put it up in space, so there's no atmospheric distortion. Great. Well, at 65,000 feet, I said you're above all but 5.5% of the atmosphere. At 85,000 feet, you're above all but 2%. Then you can produce some impressive imaging, presumably. And we have built airships that have flown this high. Now this one, it's sad, a technical glitch prevented this guy from getting up to 65,000 feet and flying for days, if not weeks. That airship flew at 65,000 feet. We don't have these flying today. The military shut these projects down. Why don't we take the knowledge of those and fly those vehicles again for science? What can you do with it? Well, this thing was built by the Southwest Research Institute down in San Antonio, Texas. It can fly 100 to 200 pound payload. Sounds very small, but you can do good science with small payloads. And this one was going to carry a 100-pound payload for 21 days. But you could build this up, and the military had made the Lockheed Martin come up with a design for a larger payload. What can you do at 65,000 feet of interest to astronomy? You can do spacecraft like ultraviolet and optical resolution and photometry. Space telescope costs billions of dollars. Even if the airship costs 50 million, you're ahead of the game. No ground station to purchase or develop, unlike a ground-based observatory. Station keeping means you don't have to have the worry about the no-fly zones around other countries. You're not flying around the pole. No weather interference. So when you schedule a Hubble Space Telescope, you know on a certain day they'll make the observation. On a ground-based telescope, you get access to a telescope. You do not get access to the object if the sky is cloudy. You're stuck. So if you're above 60,000 feet, you are above the weather. Minimum scattering of light, moonlight, we have observing on the ground. That's dark time and bright time. Bright time is when the full moon is close, and if the sky is very bright, you can't observe faint objects. When you're high altitude, that should be minimized. Horizon observing capability. There's almost no extinction when you're above all but 5% of the atmosphere, and if you're at the equator, you get the entire sky, north and south hemispheres. You can see the southern stars as well as the northern stars. And you would have simple line of sight communication. Trivial. Perfect. You have to get the telescope to be lightweight so you can lift it, and you have the pointing issue of tracking and pointing it accurately. What you can't do in a high altitude airship with a telescope is you won't get above the ionosphere, which you'll have emission lines, the night sky emission lines, the aurora lines. And you won't be able to do UV observations because you can't get above 100,000 feet. You're not above the ozone layer. Daytime observations are probably not possible because the sky is still too bright. The Earth is too bright below you. It's this brilliant blue marble below you. You can't do it. We have tried to do this with aircraft to get above ground-based observatories, but not to maybe 65,000 feet. NASA and the German government purchased from Boeing not a stretched 747, a scrunched 747. Boeing built a 747 SP to fly really fast from LA to Japan. They only built a couple of them. NASA bought it and put a hatch in the back that could roll open and expose the telescope. And this is called SOFIA, the Stratospheric Observatory for Infrared Astronomy. It's a 2.5-meter telescope. It's going to fly. It's flying now. It flies at around 41,000 feet, and it does infrared work, and it costs a bundle of money. These are old numbers. This is way. It's not $40 million a year. It's more like $70 or $80 million a year. But that's the only competitor to high-altitude airships. And if you're going to spend 40 or 60 or $70 million a year, why don't you just buy one airship and put a telescope on it? There's another reason why you can compete with on high-altitude aircraft. This is a plot. I'll explain what this means. These are 4 different panels. And this is the observatory at Mauna Kea. This is the Sophia 747 aircraft. This is a theoretical airship, and that's a high-altitude balloon. And what's plotted here is wavelength, 1 micron, which is infrared light, to 10 microns, very infrared light. We emit at 10 microns because of our body temperature. And then 100 microns, this is far infrared and millimeter. And this Mauna Kea Observatory is where the Keck telescopes are, and that's 14,000 feet up. That's 4.3 kilometers up. And what this plot on the y-axis is the absorption of the atmosphere for light, for transmission of space information. And when the plot goes down, that means there's no light coming at that particular wavelength, so you can't observe there. And then there's a window here, and then it's crashed back down. There's a window here, and this crashes back down. And there's a window, so you can see light at these particular wavelengths, but not down here from, say, 30 microns up to 1,000 microns, far into the infrared, into the millimeter wavelength. Sophia, the 747 flies, and you can get, well, you made a huge improvement. You don't have all these absorptions, and you can start to do something out here. But an airship, it's almost clear everywhere. Now, that's at not 65,000 feet, that's more like at 90,000 feet, but still, you can see it a huge improvement. So airships can do great things. Well, the Hubble does fantastic stuff, but the Hubble won't be up all the year for many more years. I would love it to be up there for many more years. And as I said, what does Hubble give you? It gives you crisp images. This is a photograph of a galaxy taken with an 8-meter telescope, a huge telescope on Mauna Kea, right next to the Keck telescopes. It's the Japan's 8-meter. They called it the Subaru 8-meter, and this is the galaxy. This is the same image of the same part of the sky from space with using a smaller telescope, the 2.4-meter diameter mirror on the Hubble Space Telescope. You see the difference. One, I can't really tell what's coming, what's the thing made of. And here I have all the detail. And in a few years, we're going to miss that glorious advantage of seeing the details. So airships would allow us to do some work like this. It's a smaller telescope, but it's much crisper images. It makes all the difference in the world. A 2-meter airborne telescope could give you the same resolution as basically Hubble, we think. It would be above all the weather, so every night you could observe. You could do it night after night, day after day, as long as the platform existed at high altitudes. You could also do studies of exoplanets, planets around other stars. Here's a picture taken actually through the using the Keck 10-meter telescope at Mauna Kea, and they put there's supposed to be a really bright star in the middle, but they put an occulting disk, so it blocked it out, a disk to just block the light. And you can see these individual dots are planets around that star. You could do the same thing, easier, if you had a telescope on a high-altitude aircraft, 65 or 75,000 feet. Another thing you can do, you could do high-resolution imaging of the sun. NASA put up the Solar Dynamics Observer, a really wonderful breakthrough instrument, spacecraft to study the sun. It has many different telescopes serving the sun at many different wavelengths going into the ultraviolet. It only produces a resolution of 1 arc second. That's an indication of how sharp the images are. 1 arc second. You can do 1 arc second on the ground. You can do better than 1 arc second on the ground. Hubble Space Telescope can do about 20 times better than 1 arc second, but Hubble is not permitted to look at the sun. It will sever itself. It will burn itself up by looking at the sun. It will sever the metal structures. So we have nothing to get us high-resolution images of the sun, except for there was one flight in the last few years on a high-altitude aircraft, a high-altitude balloon called Sunrise, that they lifted up to 120,000 feet and had a very accurate pointing system, and they got high resolution. It lasted 4 or 5 days. They're about to fly it again. But come on, if you had a 2-meter solar telescope, you could get 1080i or 1080p imaging of the sun at high resolution and just feed it down every day to get really high resolution, see what the sun is really doing. This is the surface of the sun, what's called the photosphere of the sun. the region where you get most of the light, and it has fine structure to it. And if you could, this is one of the best pictures ever taken of the sun from a ground-based telescope. You could crush that by a factor of maybe 10, maybe even a little bit more than that if you had a high-altitude airship with a suitable sized telescope. So there's fantastic stuff to be done in astronomy, as well as earth science stuff. And so the conclusion of this whole thing is that airships really do offer us a tremendous opportunity to do science. Both low atmospheric earth science work, and boy, potential for great new astronomy stuff that could rival space missions. And that's been the whole point behind this Keck Institute for Space Studies workshop, opportunities for airships as unique science platforms. Thank you very, very much. Appreciate it.